All right. So what we're going over today here, okay, writing chemical equations, looking at what chemical reactions are, how we know one has occurred, okay, things like that. Now the first little bit should be a review, okay, signs of a chemical change and things like that. Then we'll go over essentially the 5 main types of chemical reactions. We'll look at how we write them out, okay, balancing and that kind of stuff. And then for the next little while, that'll be what we're working on. Okay, well, that'll be after we come back from the break, because tomorrow we're actually going to be in the computer lab working on something else. Okay, so key points for today: signs of a chemical change, know the types of chemical reactions, understand how to identify each reaction type, and then obviously learn how to write them out. All right, so in a chemical reaction, we know that one has occurred if the final products are chemically different than our reactants. All right, and just so you know, those terms, okay, mean the following. If I have, let's say, a reaction that looks like this. Okay, so that's a relatively simple reaction, but okay, if I have a reaction like that, the stuff that is being added together and is actually reacting are called the reactants. Okay, the stuff that is produced are the products. Okay, so important to know those terms. Now, I have the same elements on both sides. I've got sodium on both sides, I've got potassium on both sides, chlorine and bromine on both sides. But are the compounds I have the same? They're not, right? On this side I have sodium chloride and potassium bromide, and on this side I have sodium bromide and potassium chloride. Are these things chemically different from what I started with? They are. They're no longer paired up with the same people or whatever that they were paired up with on this side. These things are chemically different. They will have different physical and chemical properties than the stuff that was initially in the reaction. Does everyone follow me on that? Okay. You will not be able to get back what you started with if a chemical reaction has occurred. All right? You can't undo a campfire. All right? Once you have burned the wood in the campfire, can you get the unburned wood back? You cannot. Okay, a chemical reaction is not reversible. Okay, and a campfire is a chemical reaction between wood and oxygen in the atmosphere. All right, so you can't get that stuff back. You can't unburn gasoline from your car either. It would be great if you could, all right, because then you'd always have a full tank, but you can't. All right, once the reaction has occurred, you can't get that stuff back. Now, a physical change, on the other hand, is reversible. Okay, if I crumple up a piece of paper, can I uncrumple it? Yes, it's still paper. Right? I have not changed the fact that it is paper. Right? I haven't forced it to combine with something else and changed its properties. All I've changed is its shape. Right? But it is still chemically paper, and thus as a result, okay, I can get it back. If I evaporate water, is that a physical or a chemical change? It's physical. Right? I still have water. I have it in a different state, but it's still H2O. I have not chemically altered it. Okay, I've physically altered it, but I have not chemically altered. Does everyone follow the difference? Okay, really important we know the difference between a physical and a chemical change. Okay, evidence of a chemical reaction. Okay, color change, definitely. Okay, when a chemical reaction occurs, a lot of chemical reactions cause very vibrant color changes. Not all of them, okay, but many of them do. Okay, an odor change is also a sign that a chemical reaction has occurred. If you smell something after a reaction that you didn't smell before, chances are a gas was produced. Okay, now not all gases have a smell, okay, but many do. And if it smells different than it did when you started, you know that what you have has different physical properties than it did at the beginning, because odor is a physical property. Everybody follow there? State change. Now, that doesn't necessarily mean that it went from a liquid to a solid. Right? What it usually means is it went from being soluble to not being soluble. All right? Sometimes when you put two things together, and I showed you this the other day, you get a precipitate. Okay, you get that solid that comes out of the two things that were actually like solutions, and then suddenly this solid forms out of nowhere and falls to the bottom. That's usually what we mean by a state change. The other thing that could be is you could have something turn from a liquid to a gas. It's possible that that could happen during a chemical reaction. Okay, and lastly, an energy change. Most chemical reactions involve some change in energy. They either get warmer or they get cooler. Not many get cooler, okay? But a lot of them get hotter. All right, as a result, there's an energy change. Energy is either released or it is absorbed. All right, if the energy is absorbed, it'll feel cooler. If the energy is released, it'll feel hotter. Everyone follow? Okay. All right, so there's generally 5 types of chemical reactions that we'll go over. There's more than that, okay? But generally there are 5 sort of simple types. Okay, the first type is the simplest. If I put two things together, I am synthesizing or making something new. That is a synthesis reaction. Okay, so if I have 2 reactants and only one product, I have undergone or performed a synthesis reaction. Usually a synthesis reaction involves putting 2 elements together to form a single compound. But it can on rare occasions be 2 compounds forming a single compound afterwards, but that's pretty rare. All right, so most of the time a synthesis reaction will look like this one. Okay, an element like potassium reacting with another element like bromine, okay, to produce potassium bromide, a single compound. Okay, so synthesis reaction, 2 or more elements, okay, react to form an ionic or molecular compound. Okay, 1 ionic or molecular compound. Okay, the S's and G's here, okay, they stand for the state of matter. So this is saying that this magnesium here is solid, okay, this oxygen here is a gas, okay, and that this magnesium oxide is solid. In Science 10, you actually don't have to write the states of matter in your chemical reactions, so you guys won't see that often in your reactions. Now, when I'm looking at this reaction here in the white box, okay, how many atoms of potassium are there? 2. How many atoms of bromine are there? 2. How many molecules of bromine are there? 1. Okay, do you notice the difference here? Notice that the 2 atoms of potassium are separate, but the 2 atoms of bromine are attached. Okay, some elements are what we call molecular elements. It doesn't mean that, obviously they can be in a molecular compound, but it also means that they bond with themselves. And when they're in their element form, they actually come not as single atoms, but as molecules. All right? So when bromine is by itself, it doesn't come as single atoms, it comes as molecules of 2 atoms of bromine. Okay? Everybody with me there? Now if you look on your periodic table, those atoms are all highlighted for you. Okay, the yellow highlighting on your periodic table shows all the ones that are molecular elements that come as pairs. All right, and so that's going to be nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and astatine, as well as hydrogen. Okay, all of those, when they're by themselves, not in a compound, come as a pair. All right. You will also see that phosphorus is highlighted, I believe, in orange. Yes? Sorry, blue. All right. Phosphorus is highlighted in blue because it comes in sets of 4. So whenever phosphorus is by itself, it actually comes in sets of 4 atoms combined into one molecule. All right, so it's the phosphorus quadruplets. Okay, all of these other ones are twins, and sulfur comes as a molecule made up of 8 atoms of sulfur, the sulfur octuplets. Okay, everybody follow me there? All right, they're highlighted on your periodic table, so you don't necessarily have to memorize which ones are the special ones and which ones aren't. Just know that that's what those colors mean on your periodic table. So in this reaction here, I have the 2 atoms of potassium reacting with the molecule of bromine, and then on this side, I have how many molecules of potassium bromide? Okay, here's an atom of potassium, here's an atom of bromine. There's one molecule, there's the other molecule. All right, that's what this 2 stands for. There are 2 molecules of potassium bromide on the other side. Okay, everybody with me? All right, so big numbers, okay, they mean multiply whatever you have here by 2. The little numbers, okay, imply that, again, there's a multiplication by 2, but only of the one thing. All right, and if they're little like this, it means that they're bonded together. All right, the exact opposite of a synthesis reaction is what happens when something breaks down. Okay, when something breaks down, we often say that it's decomposing. All right, so a decomposition reaction happens when a compound or a molecule isn't stable enough to stay as a molecule. So it breaks down into its parts. Okay, usually that means it breaks down into 2 elements. Occasionally, it can mean it breaks down into many things. Okay, a couple of elements and a couple of compounds, depending on how big the molecule is. All right, so in this case, here with this first one, we have water breaking down into hydrogen gas and oxygen gas. Okay, obviously that doesn't happen very often in nature, but it is a process that happens artificially in order to produce rocket fuel. Okay, what they do is they run an electric arc through water, which separates the hydrogen gas from the oxygen gas, okay, or essentially breaks up the water molecule, turning it into those 2 gases, and then those are used to power the space shuttle, okay, or the Soyuz capsules, or whatever it is they're shooting into space. Okay. All right, on this side here, in the reactant side, how many hydrogen atoms are there? There's 2 in each molecule of water, but how many molecules of water are there? Okay, all right, so what this means is this. This big 2 here means there are 2 molecules of water. And in every molecule of water, there are how many hydrogens? 2. So how many hydrogens are there? 4. Okay, so that's what these numbers, or how these numbers work. All right, the big 2 means, okay, or the big numbers mean multiply everything in the compound behind me by 2. All right, so over here, do I still have 4 hydrogens? Yeah, is that important? Should I have the same amount of stuff on the product side as I have on the reactant side? What do you think? It is crucial that you have the same amount on both sides. If you don't, you have broken the #1 law of the universe. The law of conservation of mass. If you suddenly have more than what you started with, you are God. Because you have created something from nothing and magically ended up with more than you began with. All right? Can you do that? The answer is no, in case you were actually wondering. Okay? You cannot magically create something from nothing. All right? By the same token, you cannot destroy anything either. So I can't suddenly have less of something on the other side of the equation than I started with. I always have to account for everything. An equation has to be balanced. That means there has to be the same number of everything on each side of the reaction. All right, so in this case, there are 4 hydrogens and 4 hydrogens. Okay, how many oxygens are there over here? 2. There's 1 in each water molecule, and there are 2 water molecules, so that's 2 oxygens. How many over here? 2. Okay, so it's balanced. We're good. Okay, looking at this reaction here, it's another example of a decomposition reaction. Okay, nitrogen triiodide is decomposing into nitrogen gas and iodine liquid. All right. Now, when that happens, we get a molecule of nitrogen gas. Okay, that's what the little 2 means. The 2 nitrogen atoms are bonded together, and 3 molecules of iodine liquid. Okay, again, this little 2 means they come in molecules of 2 atoms each, and there are 3 of those molecules. So on this side, how many iodine atoms are there? 6. 3 times 2, right? Each molecule has 2 atoms in it. So there's a total of 6 here. Okay, are there 6 over here? Yeah, 2 times 3 is still 6. Okay? How many nitrogen atoms over here? 2. Okay? There's no number next to nitrogen, so it's a 1. 2 times 1 is 2. There's the nitrogen. There's the nitrogen. And on this side, there's a nitrogen, and there's a nitrogen. There's still 2. All right, everybody with me? Okay, so a decomposition reaction, a single compound breaks down into 2 or more parts, usually elements. Okay, questions on that one? All right. Sorry, I had this here to show you the highlighting, but we've already done that. Okay, so the pairs of things: nitrogen, oxygen, fluorine, chlorine, bromine, iodine, astatine, and hydrogen. Okay, are the pairs. Okay, the quadruplets are phosphorus, and the octuplets are sulfur. Okay, so just make sure you've got those highlighted on your periodic table. Okay, another type of reaction: combustion reactions. What gas has to be present for something to burn, Zach? Okay, oxygen has to be present. Okay, in a combustion reaction, you are always going to have what we call a hydrocarbon reacting with oxygen. A hydrocarbon is exactly what it sounds like: carbon and hydrogen. Okay, so anytime you have a compound that has carbon and hydrogen in it reacting with oxygen, you're burning something. Okay, you're burning it, and you are producing what is produced in every single combustion reaction. It does not matter what you start on fire, you are producing the same things: carbon dioxide and water. Okay, so the nice thing about combustion reactions is the products are always the same. You will always make carbon dioxide and water, okay, in a combustion reaction. Okay, so those always remain the same. Now, there's some special rules when you're dealing with a combustion reaction, okay? And it has to do with making sure you have the same number of everything on both sides, okay? We'll go over that in a little while. We'll skip it for now, and we'll talk about it in a few minutes. Okay? But in this reaction here, let's make sure we actually have everything balanced. How many carbons are there on this side of the reaction? 3. How many over there? Still 3, right? 3 times 1 is still 3. All right. How many hydrogen over here? 8, right? How many over here? 8. 4 times 2 is 8. Now here's the trick. How many oxygen over here? 10. How many on that side? Okay. Is oxygen in 2 different places? Is that okay? Yes, as long as it adds up to the same number I have over here. There's 10 over here. Okay. 3 times 2 is how many? 6. Plus 4 more is 10. Still works out. All right. Again, it's a matter of, do you have the same amount on both sides of the arrow? Doesn't mean it's only going to be in one place. It could be in a couple of different places. All right. As long as it still adds up on both sides. Okay. So this combustion reaction here is the combustion reaction that occurs in a propane-powered barbecue. Okay. C3H8 is propane. All right. If you have a lighter that runs on butane, okay, that's C4H10. Right, so stuff like that. They're fairly common things. All right. So the big thing here to remember, you're going to have a hydrocarbon and oxygen on the reactant side, and you're always going to have carbon dioxide and water on the product side. Okay. There's 2 kinds of replacement reactions: single replacement and double replacement. The thing you need to know about replacement reactions is they always involve only ionic compounds. Molecular compounds are never involved in a replacement reaction of any kind. Okay? The reason being, there has to be a trading of charges and electrons, and that doesn't happen with molecular compounds. So replacement reactions only involve ionic compounds and elements. Okay, so in this case here, we have a single replacement reaction. It's called a single replacement reaction because one of the elements is single. Okay, it does not have a partner. This is a compound. This is a metal and essentially a non-metal. That's a couple. Okay, everybody follow me there? Yes? All right, so what happens in a single replacement reaction is this. The thing that's by itself replaces whatever is like it in the ionic compound. So an ionic compound has a metal, silver, and a non-metal, nitrate. What's copper, metal or a non-metal? It's a metal. So who's it going to replace? Silver. Okay, so we always look to replace the things that are alike. Because what has to happen is we have to end up with an element and an ionic compound on this side. All right, so if I said, no, the copper is going to replace the nitrate, I'd end up with nitrate by itself, which can't exist by itself, and I'd end up with two metals bonded together. And metals don't bond together. Okay, everybody follow? If this was a non-metal, and I swapped it out with a metal, I'd have two non-metals together. What kind of compound does that make? Two non-metals are a molecular compound, and those can't exist in replacement reactions. Okay, so you always have to replace the things that are alike, right, so that you always end up with an ionic compound. Right, so the analogy I always use is you got this guy here who's by himself, and you got this couple dancing. This guy decides she's pretty hot. Okay, this guy, not so cool. So he goes and rolls him, gets him out of the way, takes off with his girl. This guy winds up alone. All right, so what we get is a new couple and a new lonely person. Okay, everybody follow? I'm not saying you should do this in real life. Okay, I'm just saying that this is what chemicals do. All right, now the other thing you have to remember is chemistry is very old-fashioned. You notice it's not the two guys dancing together over here. Okay, I have to get an ionic compound, a metal and a non-metal together, always. Okay, can't be two girls together, can't be two guys together. It's got to be a metal and a non-metal always when this happens. Everybody follow me there? Okay. Now let's look at balancing here and make sure that we've got this reaction balanced properly. How many copper over here? 1. How many copper over here? 1. Okay. How many silver here? 2. 2 over there. Okay. How many nitrate here? See, that's the thing. When it comes to the polyatomic, we start getting screwed up. Okay. Nitrate is NO3. How many NO3s are there? 2. There's 6 oxygens. Okay. The 3 only applies to what? The oxygen. It doesn't apply to the nitrogen, right? Nitrate is NO3. There are 2 of them. How many nitrates over here? 2, right? The brackets say everything in the brackets is multiplied by 2. All right? So that's kind of where we get a little bit messed up. We start kind of over-applying the numbers. Little numbers only apply to the element that they are immediately following. All right? The big numbers apply to everything behind them. Okay, important to remember that little part. Okay, so a double replacement reaction then is exactly as it sounds. Now there's no lonely people. Okay, there's 2 couples. Don't take that example too far though, okay? Okay, there's 2 couples, and when we're done the reaction, there'll be 2 different couples. All right, we have an ionic compound that's reacting with another ionic compound, and when we're done, we get 2 new ionic compounds. So this reaction here starts with calcium chloride and sodium carbonate. But you can see that on this side, calcium has a new partner. Okay, it was with chlorine over here, now it's with carbonate. And sodium, likewise, has taken calcium's partner, and has ended up with chlorine over here. All right, so the general rule when you're dealing with a double replacement reaction is this: swap the metals. Okay, all you have to do is swap the metals, and you've got your new compounds. Everybody all right with that one? Okay, that's your 5 reaction types. Okay, we're only going to deal with those 5. Let's double check and make sure that this reaction's balanced. Okay, so I've got how many calcium here? 1. How many over there? 1. Okay, how many chlorine here? 2. How many over here? 2, right? This 2 applies to everything. That means there's also 2 sodium, and there's 2 sodium over here. How many carbonate here? 1. Carbonate is CO3. How many CO3s are there? 1. Okay? There's 3 oxygens in carbonate. Carbonate is CO3. There's only 1 carbonate here. You guys follow the difference? All right? Over here, okay, there's still only 1 carbonate molecule. Okay. All right. Now, when you're communicating a chemical reaction, okay, obviously the first thing you want to do is make sure that you've got all of the compounds matched up right and that you've swapped and dropped them all correctly and all of that kind of stuff. Okay? But you also need to make sure that you have balanced it, and that's what we've been talking about all the way through. Making sure that there's the same number of each type of atom, excuse me, on both sides. All right, so this is kind of a tougher one. How many nitrogen here? 3. How many nitrogen on this side? 3. 2 times 1 is 2, plus 1 more is 3. Okay, it doesn't have to be in the same place, but there's 3 there. Okay, on this side, there's how many oxygens? On the reactant side? 7. 3 times 2 is 6, plus 1 more is 7. All right, over here, 2 times 3 is 6, plus 1 more is 7. All right, and on this side here, there's 2 hydrogens, and over here there's 2 hydrogens. So that reaction is balanced. Okay, so a balanced chemical reaction, okay, is one in which the total number of each kind of atom or ion is equal on both sides. Okay. This is where being able to write the formulas for a compound or the name for a compound becomes crucial. Okay? If you can't figure out the formula for a compound from its name, you will probably not be able to write the reaction properly. All right? Because when you write out the formula wrong, you won't be able to make the equation balance. All right? So if you can't make an equation balance, chances are one of your formulas is wrong. All right? Always a good indicator. If you can't make a reaction balance, go back and check and make sure that all the compounds are right. Swap and drop them again. Double check your prefixes, all of that kind of stuff. All right, here's what I want you to do. We just went over 5 reaction types. So I want to combine reaction types with writing the proper names of chemical compounds. Okay, I also want you to try and balance these reactions. Okay, so I want you to show me what type of reaction it is. Just write the type. Okay, synthesis, decomp, single replacement, double replacement, or combustion. Okay, write out the names of everything, and then try and balance the equation. Okay, probably the balancing part will be the part that will throw you off right now because we really haven't gone over how to do it. Right? But give it a try. See how many of these you can get. I'll give you, actually, let's just say do the first, well, don't do that one because we already did that one as an example. Do the first 2 here. Okay, so do the N2 plus H2 and the CH4 plus O2 one. Okay, do those 2. I'll give you a couple minutes, then we'll go through them. So number 1, I've got nitrogen, which is an element, reacting with hydrogen, which is an element, and they're producing a single compound. What kind of reaction goes that way? Synthesis. All right, so this is a synthesis reaction. Okay, I need to write out the names. So nitrogen plus hydrogen. Okay, gives me nitrogen trihydride. Okay? Because these are elements, they don't require prefixes on them. Okay? A lot of people like to write dihydrogen and dinitrogen. Okay? Well, that's not the way that those work. All right? Now, we need to balance this reaction. Okay? So we need to make sure that there's the same number of everything on both sides. There's a couple of little tricks for making sure that that works right. Okay? The first trick is generally start with whatever is present in the largest number. Right? What's present in the largest number in that reaction period? Which element has the biggest number beside it? Hydrogen, right? There's 3 hydrogens over here. There's 3 on this side, but there's 2 on this side. And I need to make sure there's the same amount on both sides. What's the lowest common multiple of 2 and 3? No, lowest common multiple. 6, right? The lowest common multiple of 2 and 3 is 6. So if I take 3 here and go 3 times 2, does that give me 6? Okay? And if I put a 2 here, 2 times 3 is also 6. Agreed? All right. Now I have 6 hydrogens on both sides. Is that what I was looking for? Right? They're balanced now. There's the same amount on both sides of the arrow. Okay? This 2 also means there's how many nitrogen? 2. And, look at that. There's 2 over here. Do I now have the same amount of everything on both sides? Yeah. Okay? That's how you balance a chemical reaction. Start with whatever's present in the largest number. There's always an exception for every rule, unless that happens to be oxygen. Okay? And balance from there. All right? You may have to do some multiplication. Here's the thing. You cannot change the little numbers. Right? You can add big numbers. We call them coefficients. Okay? You can add coefficients, but you cannot change the little numbers. All right? Those are set because you've maybe swapped and dropped an ionic compound to figure out what they were, and you can't change them once you've done that. All right? So you can only balance by putting in more of something. Okay? That is putting in the coefficients. All right. Let's look at the third one there. What kind of reaction has carbon and hydrogen reacting with oxygen, Dominic? Combustion. All right, so this is a combustion reaction. Now, I need to write everything out. Okay, need to write everything out. So I've got carbon, and this is tetrahydride. Okay, because there's 4 hydrogens, right? It's a molecular compound. Okay, it's reacting with oxygen, and it's producing water. And you can call water in an equation. That's what H2O is. You don't have to call it dihydrogen oxide or whatever. Okay, and carbon dioxide. Okay, carbon is C. CH is carbon and hydrogen together. Okay. Now, we just talked about balancing rules for the first one. Combustion reactions have their own set of balancing rules. All the other reactions balance like the first one did, but combustion reactions are different. Okay. They have to be balanced in a special way. Okay. They have to be balanced in alphabetical order. You'll have a really hard time balancing if you don't do it in alphabetical order. Okay, so what should I balance first? Carbon, hydrogen, or oxygen? Carbon. Okay, you'll probably notice here I told you in the first one, if ever oxygen was your thing in the biggest number, don't do it. Do something else first. Oxygen you always balance last. It always messes everything up. Okay, if you do it anything other than last. Okay, yeah. Can I just get the front bank of lights shut off there? Yeah, perfect. Better? Yeah. All right, so I've got how many carbon over here? 1, okay? And I've got how many over here? 1. Oh, this is starting out good. Okay, I got 4 hydrogen over here because that's the next thing alphabetically. How many over here? 2. What times 2 will give me 4? 2. All right, so I'm going to put a 2 here. Now I can balance the oxygens. There's how many here? And how many here? 2. So 2 plus 2 is 4. And I've got 2 here, so what do I need to put here? A 2. Now we're done. That reaction is balanced. Okay, everybody follow? There's a second rule that goes along with the combustion reactions, and that is what we call the rule of 2. Okay? If you have an even number of carbons, you start with a 2 in front of the carbons when you balance, but we'll get to that when we encounter one of those. All right. I want you to try the next two. So try this one with water and this one with chlorine and sodium iodide there. Okay, so you're identifying the reaction type, writing it out in words, and balancing it. All right, let's look at the one with water here. What kind of reaction is this one? Caroline? It's a decomposition reaction. It starts with a single compound and breaks down into two elements. All right, so decomp. All right, now I'm going to write it out in words. That's pretty easy. Water, okay, goes to hydrogen plus oxygen. Okay. Again, I don't need prefixes or anything like that. This is just, I mean, it's two atoms of hydrogen, but it's just hydrogen. There isn't anything else there, so I don't change its name. Okay, same with the oxygen. Now, for balancing purposes, all right, I start with hydrogen. There's two here and two there. Hydrogen's already balanced, but oxygen isn't. All right, there's two oxygen over here, but there's only how many here? One. So what times one will give me two? Two. All right, so if I put a 2 there, that gives me how many hydrogen? 4. What times 2 gives me 4? 2. Balanced. Okay, so is the balancing very hard? Like it's simple multiplication, right? Like you can go 2 times 2 and 3 times 2. You're pretty much good. You're not going to ever have to do like 5 times 8 or anything like that. Although that shouldn't be a problem either because it's 40. But okay, hopefully you guys can all do your sort of simple multiplication tables on those. Okay, how many people are done the next one here with the chlorine? Hands up if you're done. Okay, how many people are stuck? All right, let's just go through it then. So I've got what kind of reaction here? I've got a single element reacting with an ionic compound, making a different single element in a compound. It's a single replacement reaction. All right, so to write it out in words, this stuff here is chlorine. Okay, this stuff here is an ionic compound called sodium iodide. Okay, and that's going to make iodine, the elements, and sodium chloride. All right, why can I not write salt as the name for that? Okay, because I know a lot of people do. They see, oh, sodium chloride, that's salt, and they write salt down. Here's the problem with that. Salt is a general term referring to any ionic compound. Okay, salt just happens to be the most common salt. All right, but it isn't the accurate name for that stuff. All right, so we always have to name it sodium chloride, okay, to be specific. Now I need to balance. We said we always start with whatever's present in the largest number. That could be iodine or chlorine, doesn't make any difference. Let's start with chlorine. There's how many over here? 2. How many over here? 1. So what do I need to put here? A 2. How many sodium does that give me? 2. How many over here? 1. So I need to put a 2 here. How many iodine does that give me? 2. And now there's 2 over here, and it's balanced. Usually if you've done it right, by the time you get to the last thing, you'll find it already balanced. Okay, always a good sign. All right, try the last 2 here. We should be able to get those ones done here before the end of class. Okay, so give the last 2 a try, and then we'll go through them. All right, let's have a look at our second last one here. We've got 2 ionic compounds reacting to form 2 new ionic compounds. So it is a double replacement reaction. Right, in fact, they both are. All right, then we got to write out the names. Okay, so this stuff here, ionic compound, calcium chloride. Okay, this stuff here is sodium carbonate. Okay, and that forms calcium carbonate and sodium chloride. Okay, so now we got a balance, and we said again, we start with the thing that's present in the largest number, and this will trick a lot of people because they'll go, oh, there's a 3 here. I'll start with carbonate. How many carbonates are there? 1. Okay, so I don't start with carbonate. I should probably start with either sodium or chlorine. All right, so I'm going to start with sodium. There's 2 over here. How many over here? 1. So I need to put a 2 here. Okay, that gives me 2 chlorines. And there's 2 chlorines over here. So that's balanced now. Now I can look at calcium. There's 1 calcium, so that's balanced. 1 carbonate, and 1 carbonate. So now it's all balanced. All I had to do is add 1, 2 to that. Okay. carbonate. Yeah. How many people have done the last one? How many people are stuck on the last one? Okay. So we've already said it's a double replacement reaction because all of these are ionic compounds. Okay, write them out in their name form. This is hydrogen chloride. Okay, plus potassium hydroxide. Okay, it gives us water. HOH is water. Okay, plus potassium chloride. Okay, how do I know this stuff is water? How many H's are there? 2. How many O's? 1. It's H2O. It's just written in a different order. Okay. Now, for the balancing, this one's balanced already. How do I know that? Just by looking at it. There's no numbers. Okay. There are no little numbers, no subscript numbers. That means everything in there is a 1. And if everything in there is a 1, everything is balanced because everything's a 1. All right. So anytime you see a reaction with no little numbers, you're done. Okay. It's already balanced. Now, what if that was a fill-in-the-blank question and there were blanks in front of each compound? Should you leave it blank? No, because then I won't know whether you knew how to do it or not. Okay? So, write 1s in front of everything just so I know you did it if it's a fill-in-the-blank question. All right? So, tomorrow we're going to go into the computer lab and I'm going to show you how to share your lab reports with me in Google Docs, okay, and Google Drive and all of that kind of stuff so that you know how to do it over the week off break because it's due when we come back. Not right away, obviously, but on the Tuesday when we come back. So make sure you're getting to work on that, okay, and watching the podcasts, plural, okay, of all of those things related to the lab. Okay, really, guys, I've laid that lab out for you and essentially given you all the answers. If you spend the time watching the podcasts, you really can't go wrong on the report. But it will take some time and effort on your part.